Okay, so the next talk is from Christophe, who will be talking about MCFOST, the radiative transfer modeling.
Thank you. Hi, everyone. For those who don't know me, I'm Christophe. I'm not going to discuss much about science today. I'm just going to present MCFOST so that you get an idea of what you can do, what you can't do, and how it's different from my grid, maybe. How it's worse or maybe better. So MCFOST is a 3D relative transfer code. It uses the Monte Carlo method to sample the specific intensity. In the region where it's very optically thick, it can use some diffusion scheme, and the observable are produced using a ray tracing method. And it does a relative transfer in dust and in gas, so in continuum and line. So it does multiple scattering and polarization. You have dust heating and cooling, non-LT atomic and molecular population level. And if you need to, there's some Zeeman splitting now. So a few specificities of the code is that each cell in the code is completely independent from the other one. So you could have a grain size distribution that's different in every single cell. You can have different dust property. You can have ices in some part of your model, not in other ones. So you can basically build a model doing whatever you want. So you can post-process a phantom simulation with different grain sizes everywhere, for example. There's no limit on opacity for the grids for which there's a diffusion approximation, which is not all the grids, and I'll discuss that later. And we've tested it on a cylindrical grid, for example. You can go to 1 billion in optical depths, and there's no problem to compute the temperature in those cases. But that doesn't work yet with phantom, for example. You have non-equilibrium grains, so if you're interested in like pHs, for example, with the James Webb, which hopefully going to be helpful for that. And we can, in most cases, be consistent in the dust and the phases, in the sense that if you have line emission, it's going to be reabsorbed by the dust. And if you have infrared emission from your dust, it's going to pump your level of your molecule, for example. There's work in progress doing very similar to what you discussed in doing machine learning to try to speed up the chemistry and the gas thermal balance. So we have a large database of ProDemo models, and we're using random forest to do that, but it's similar, I think, in idea of what you're trying to do to basically speed up the calculation and be able to have an on-the-fly chemistry. And we can couple to some codes. You have a bunch of them, the main one being phantom, of course. So you can produce a variety of observations, scatter light images, polarization maps, thermal emission maps, for example, for ALMA, spectral energy distribution, and molecular and atomic emission maps, as well as post-processing. You can compute visibilities if you want to see what your object looks like with ALMA in the UV plane or with Pioneer gravity or whichever instrument you want. So the thing I'm mostly going to discuss today is the work we've been doing with Daniel over the last few years, trying to couple it with Phantom. So the main application so far is still post-processing. So you run your Phantom model, you post-process it, and because, like Margaret, it uses a Voronoi mesh, there's no interpolation between Phantom and MCFOST. But potentially the most interesting thing in the next couple of years is that now MCFOST can be called directly from Phantom as a library. So you basically just have one command line where you pass your SPH particle properties, the position, velocity, number, density, or for different grain sizes. MCFOST will do the tessellation on the fly, the relative transfer, and return the dust temperature. In the long term, potentially to the gas temperature with the machine learning. And we can compute radiation pressure, even if I think it's not turned on at the moment. It's relatively fast, except in some cases if you have some very dense clump or something where the Monte Carlo packets get trapped, and it can get very slow. But we're working on that. And the idea is that we can perform that every few time step, with few being could be a lot, but for disk, for example, we managed to run it if you have a planet in the middle of the disk, roughly 100 times per planet orbit, which should be enough for at least what we want to do. So the main game we have been playing in the last couple of years with Daniel is trying to measure the mass of planets in disk. So here you have a observation with ALMA, and you have a kink there. So if you have a disk that's perfectly Keplerian, you expect to have a nice, smooth iso velocity line, but we have a small kink, and we're putting planet, and we're trying to using phantom and MCFOST to measure the mass of the planet. So when you have a small planet, you have a small kink. When you have a big planet, you have a big one. And we're trying to basically think, well, in that case, given the amplitude of the deviation there, we have something between 2 and 3 Jupiter masses. So that's one of the main applications we have been using the two codes so far. The second one that I think is important too is they've done some comparison of live relative transfer between Ramses and MCFOST. This is for a well-known disk benchmark. So MCFOST is in red, and you can see the significant differences. This is the radial profile, so temperature is a function of radius, and temperature is a function of altitude in the disk. So in particular, in the vertical profiles, there's a lot of difference between MCFOST in red and simpler scheme like the FLD or even a FLD plus a moment one approximation. So potentially, there's a lot of improvement that we can get there by having proper temperature structure in the disk. So I don't need to discuss that because it's basically like migrate. You have Voronoi tessellation, which is very convenient. And the reason that it's convenient, I'm not going to go through the math, is that it's very easy to propagate a packet or array across a Voronoi cell. So it's very simple math. And it doesn't require to store anything. You don't need to know where are the interfaces between the cells. So it's very it doesn't use a lot of memory, so it's very efficient, even if you have a lot of particles. And I should have added migrate there, but there's a lot of code who are doing that now. And that's what it looks like, basically. So in that case, it's a 1 million particle simulation of binaries. It's HG 100-142 from Daniel's paper. And you can see that it looks very nice in thermal emission because we're probing the midplane where we have a lot of resolution in SPH. But of course, one of the problem is when you go high in the disk in scattered light, you start to see the Voronoi cell. So we're losing a bit of resolution there. And we can do the same thing in inline emission. That's from Daniel's paper. And you can do fun stuff like Beck has been doing, and maybe you're going to talk about it later. It's like you can tilt your disk and cast shadows, which look like TW Hydra, for example. So you can have like you can see the shadow in the disk. You have a two vertical cut of the temperature profile at two opposite parts of the disk, and you see that in purple and in green, the temperature are shifted. Something we did a while ago with Daniel that we should try again now is running star formation thing, where you have a cloud collapsing, you can do properly the radiation. So that's something we should potentially try to revive or at least discuss this week if some people are interested. That's something that I need to write. So the idea is try to find the difference between the four plots. And the good thing is there's none. So these are 4 disks that are starting from phantom with 4 very different aspect ratio, and you let them evolve with phantom plus MCFOS until they reach hydrostatic equilibrium, and you can see that we basically get the same answer. So the coupling between the two codes is working pretty well, which I think is good. So the next thing I wanted to discuss is basically what you discussed just before, and I think we should sit down and talk together, is to computing the gas temperature is much more complicated than computing the dust temperature because you have a lot of different heating and cooling mechanism. And you can see that that's for protoplanetary disks. It could be very different, even at scale height between 0.2 and 0.3, where you still see some emission. For example, you can expect the 12 CO to come roughly from here. So there could be some effect in the emission that you see even with molecules with ALMA. And one of the problems is that to compute the gas temperature, you need to deal with all those different heating and cooling mechanisms, and it's basically a nightmare. And not only it's a nightmare, it's also take a very long time. So this is pro-demo models for a 2D model of 100 by 100 grid points, I think. So only 10,000 points, and it takes a couple of hours. But then the main advantage is that once you get the thermal structure of the gas, you can compute all the abundances, evolve your chemical network, and make some predictions that are potentially useful. So the idea that we had was exactly the same idea, is to bypass all of that by using some machine learning. So here you have, for example, the real gas temperature and abundance of the CO molecule in the disk. So you see that the CO is frozen out in the midplane. It's photodissociated in the upper layer of the disk, and you have this weird finger in the temperature structure of the disk that a simple machine learning random forest can reproduce very nicely. And of course, it's really fast. It takes 50 milliseconds instead of 2 hours. So even if we extrapolate to 1 million cells, it would just take a couple of seconds to run all of that. And it works for a lot of things. Different molecule, H2O, HCO+, the electron density, which could be useful if you put some magnetic field in your phantom model. And you also have the heating and cooling rates if you want to do it with time-dependent radiative transfer. So it seems to be working quite well, but the same thing, I started that a long time ago and it died. So I'd be happy to discuss so we maybe can revive it. And the other thing I wanted to do is give some advertisement for Benjamin. So Benjamin has been doing a lot of work on MCFOST in the last 3 years. He's basically implemented full non-LTE atomic line transfer in MCFOST. And you can do fun stuff like having a model of the sun in MCFOST now. So this is the sun, and so you have the density and the departure from LTE. So the density is decreasing that way. So this is the upper surface of the disk, and this is one solar radius, basically. You can see that at the photosphere, you get LTE, but when you move to the chromosphere, you depart very strongly from the photosphere. And you can make some fancy plots, like finding where Lyman alpha is produced in your atmosphere or H alpha as a function of the distance from the center of the line. And you can get a nice spectrum of the sun with MCFOST, which I think is cool. So the main goal of this work is to do magnetospheric accretion model. So this is a Pluto model of a magnetic star interacting with the inner disk, and you have the accretion column. And Benjamin is mostly interested in seeing what will be the signature in H alpha and all the hydrogen line, really. And you can see that as function of the line, of the position in the line, the emission looks very different. And it is interested in seeing how that would look like with gravity, for example. So Benjamin has been doing most of the work on MCFOST in the last couple of years. So the thing I want to discuss with you this week is the most important thing I need for MCFOST. So the first one is, of course, the logo, so that I can also have stickers. Second, it's not fair that Phantom has stickers and not MCFOST. So the other thing is, so we've started to work on that last week, but I think is promising is to solve this problem of having the Monte Carlos that become very slow when you're very optimistic on the Voronoi mesh. So we can implement a modified random walk, which is fairly easy, which would make it much faster. And point 3 is basically the follow-up of that, is to use a diffusion approximation on a Voronoi mesh, which would make it even faster. And following the discussion last week, that's the thing I would really like to implement this year, and I think it's fairly straightforward. So we could have full time dependence in MCFOST to have proper cooling, for example, for gravitational instability. As discussed, I would like this machine learning thing, which seems promising to become useful. So if we can do something with that, and there's some interfaces in some part of the code that are missing. So if someone is happy to help with that, that'd be great too. That's it. Thank you very much.
Thank you, Christophe. Questions?
Just a quick one. I'm curious about what algorithm are you using for generate the Voronoi mesh?
To create the Voronoi mesh?
Yeah.
I'm using Voro++, which is a library.
C++?
Yes.
Okay.
So I have a question about the line radiative transfer. So are there any limitations in MCFOST for more like complicated like molecular structure, hyperfine structure, large number of levels, overlaps?
No. So of course, if you have overlap, no. So Benjamin dealt with that. The problem is that if you have many levels, the matrix become bigger and bigger, so it gets slower. But in practice, there's no limitation as long as you can calculate your abundances and you have all the atomic or molecular data, you should be able to run it. Yeah.
And sorry, is it LT or non-LT?
Non-LT.
Cool. Other questions? No?
Cool. Easy.
Okay, well then we'll have our coffee break.
Sorry. Oh, hello.
Yeah, we might just come back a bit early. We've only just had an hour since lunch.
Hello.
Oh, is Conrad here?
Hello.
Conrad's
Oh.
not here. So, well, if Conrad's here, any questions on Zoom?
Yeah, I've got a quick question.
Hang on.
Hello.
Hang on. All right.
Yeah, who's someone saying hello?
Yes, can you hear?
Yes, we can.
Oh, okay, good, thank you. Just a quick one. So I just want to ask, I just realized that this MCFOST is being done using the life analysis in Phantom. So it's more like a post-processing by the end of the evolve step, right? So rather than being the end, like updating the, does it update the internal energy when it heats it?
Does it update what? Sorry?
So does it like update the internal energy of the particles, like heating it, when it's doing the live analysis?
In the live analysis, it's only...
I can't hear. Sorry, I can't hear you.
In the live analysis, it's only sending back the dust temperature. We're not sending back the gas temperature yet.
Okay, so it's not like updating the particles on live.
It is, but it's making the assumption that the gas temperature is the same as the dust temperature.
Okay, all right.
But each particle has its own independent temperature, yes.
Okay, but that update is still being done within the live analysis. That's it?
Yes, yes.
So it's not like unlike the other bits in the code within that stepping where it's updating those internal energy. So as in, for example, like
I think so. Yeah, it's so MCFOST is sending back a temperature to Phantom, and I think from that Phantom computes an internal energy.
Okay, no, I was just like thinking about at what point within that code it does that. So because I can see the rest of the other heating and cooling routines tend to be within the stepping, and there's some photoionization, photoevaporation thing within the riff as well. So is it fine to have? No, I was just wondering if it's okay to have the updates being done in like at different places within that stepping.
I can clarify this a little bit. So what we've done in most of the publications to date is we just override the temperature in Phantom with the result from MCFOST, and then we don't change it between the calls to MCFOST. What we've just been doing recently as part, we tried it out in Ellie's paper, is to include the shock heating from Phantom. So any heating and cooling in Phantom is used as a source term in MCFOST to basically emit photons. So that's still a kind of equilibrium approximation. We're actually trying it out with SAL on a self-gravitating disk. SAL here? Yes. So we were trying that this week to see if we can get self-regulation going with the live MCFOST feedback. But that's a new thing. So where we're trying to use the heating and cooling. But basically, we're just computing it in Phantom, sending it through to the ready to transfer code as a source state.
So it's okay to have the heating being done at different places in the code. So that's fine, yeah.
So it's experimental, I think would be the right way to put it. So we're trying this out at the moment with mainly with SAL.
So at the moment it does work. It can update the internal energies. There's just some issues with, I think, some initial conditions that make it problematic for a gravitational stable disk.
Okay.
Yeah, I just wanted to know, you showed that for H over R, you get to some solution at some point. What happens if you have azimuthal asymmetries in the disk and then they start moving? How do you handle that? Like, let's say, for example, you have a dust horseshoe in the disk, you compute with MCFOST the temperature, and then that thing will start moving. Does each particle keep the temperature you computed at that point? Or how do you handle that thing, like something which would change with azimuth, not only vertically?
Well, the answer is we should run the radiative transfer as often as we can.
So presumably for that case, you need to have to
probably
sample like a fraction of
Yeah.
that orb at the orbit at that location.
So you need to make sure the time difference between two calls to MCFOST is much shorter than any dynamical timescale you're interested in short.
Okay, because if you're a particle and you start moving, you don't keep your temperature as you move, or you do?
Yeah.
Okay. So if I don't call MCFOST ever again, that hot banana will move around the disk. All right. And do you expect to see something different at that point? And for that, because you showed that for H over R doesn't change much. The initial condition you start with, you always get to that kind of solution. Do you expect changes in H over R at a specific azimuthal location in the disk using MCFOST, the coupling you were mentioning?
Yeah, I think so. You can if you have shadows and things like that. Definitely, yeah.
Because that would be like a specific case where perhaps the coupling can give different answers.
Yeah, I think so.
So you asking basically how to live simulation with a binary dimension.
Yes, correct. You read my mind. But did you have dust in that case? No, that's the point. I mean, it's like doing the Ragusa thing, like 2017, 18, or the HD 14257 that you did, but taking into account the coupling and see if something changes in that azimuthal sector of the disk. Because that's something like I've been talking with Francois Menard many times, like to see if you have a change in H over R at a specific location in the disk, a vortex, binary induced trap or whatever. What's the, I think you're getting there with the coupling that you have between Phantom and MCFOST.
I mean, you probably do, yeah. There must be a difference. Unless you have something in the center that create shadows and mix stuff, but
yeah. Okay, thanks.
So we definitely were interested in shadows, which basically didn't work. We didn't get any spirals to the shadows. But we simply can try this. So if no one else wants to say anything, it's coffee time, and we'll come back slightly earlier than planned.